Okay, so we're going to take a look at another electromagnetics question. We are told to calculate the force exerted on an electron close to the Earth's surface, moving at 1.5 times 10 to the 7 meters per second by 1. The Earth's gravitational field, 2. The Earth's fair weather field, and 3. The Earth's magnetic field. Alright, so first we'll deal with part 1. We'll deal with by Earth's gravitational field. So here we're really just looking for F equals ma. So we just have F equals ma where the acceleration is gravity. So this is going to be the mass of an electron. Now this will be, let me confirm this number. Don't have this number in front of me. This will be, mass of an electron is this is 9.1. 9.1 times 10 to the minus 31. 9.1 times 10 to the minus 31 approximately, multiplied by the value for G at Earth's surface level. That's about 9.8. So this is about 9.8. So we get 9.1 times 10 to the minus 31 times 9.8. This is about 8.918 ... times 10 to the minus 30. And this is newtons. So this is the value of the field approximately, the value of the force from gravity at Earth's surface level. It's just an approximation, but that's what we've been asked to find. Now we need to calculate the force exerted on the electron by the fair weather field. So the fair weather field, when we're calculating the force here, we have to make sure that we're orienting the fair weather field in the correct way. The Earth's weather field does change orientation depending on the weather. So if it's particularly stormy, the direction of the field is different than if it's not. So the fair weather field normally goes down. So we'll draw a little diagram here. Fair weather field normally negative charged on the surface, positive charged in the higher levels of the atmosphere. So we have a downwards direction here. Now this is an electron, so the electron is going to go up in the fair weather field because it's trying to get away from the negatives, right? It's trying to get towards the positives. Negatives attract positives. So here we have an electric field, and now we need to calculate the force due to the electric field. Well, this, we're going to calculate the acceleration of the electric field multiplied by the mass. Well, as it turns out, ma, so as the case for electric fields, ma is actually equal to E times Q, field times the charge, but m times a is the force. So the force here is actually the field multiplied by the charge. Fair weather field is usually about 100. So that the approximate value for the fair weather field is roughly 100. It can vary anywhere from 100 to about 300. Sometimes you'll see values like 500, sometimes you'll see values like 50. We're going to use 100 as our field strength calculation value. So we get 100 multiplied by the charge of an electron. Now the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 19. So 100 is 10 squared, so this will be about, we could make this minus 1.6 times 10 to the minus 17. And this is going to be newtons. Now for all of these, we've not been told to find the direction, so we actually don't care about the direction, we only care about the magnitude. The magnitude of the gravitational force is about 8.918 times 10 to the minus 30 newtons. The magnitude of the electric force due to the fair weather field is about 1.6 times 10 to the minus 17 newtons. And now we need to think about the Earth's magnetic field. So here we're going to have to make a few assumptions. The first assumption we're going to make for the magnetic field is that the strength is about 50 microteslas. So we're going to say 50 microteslas. This is an approximate number. You could use numbers anywhere from 1 microtesla up to 1,000 microteslas. Depends where you are, depends how strong the field is, depends what's happening at the time. This is the number we're going to use. If you're not given a number, just looking up a number and taking that number from some reliable source is going to be perfectly fine, because that's how physics research would work anyway. You would find some research paper where someone said the particular field in this area is usually this, and then you'd cite that number. Now we have to assume certain things about the particle. We could assume, in the worst case scenario, it's moving in the direction of the field, and by worst case we mean lowest possible force. The force due to the field in the case where it moves in the direction of the field, which we'll say d in B, is going to be 0. So 0 newtons is possible. We also want to consider what happens if it's moving at right angles to the field. So in a direction which is orthogonal, at right angles to the field. So we have f of B is equal to the charge times the velocity times the field times sine of the angle between them. We're going to assume this is 1 in this case. So we're going to get charge, which is minus 1.6 times 10 to the minus 19 times the velocity we were told was 1.5 times 10 to the 7. Then we need to multiply this by the field. Now we have to be very careful to convert this correctly. This is microteslas. So we're going from microteslas to teslas. Now this is usually a movement of 1 million. You can always get a machine computer to confirm this number for you. It's going to be something like, the 50 microteslas will be like 5 times 10 to the minus 5 or something along these lines. So we have 5 times 10 to the minus 5, yep. I always like to confirm these rather than assume that I am correct. So we have minus 1.6 times 10 to the minus 19 times 1.5 times 10 to the 7 times 5 times 10 to the minus 5. This gives me minus 1.2 times 10 to the minus 16 newtons. When we take the absolute value of this, this is 1.2 times 10 to the minus 16 newtons. So we're able to find the magnitudes of the forces due to gravity, due to the fair weather field, and due to the magnetic field. And this is how we do this question. This is one way to do this question.